Okay, so my name is Yuhao Ye, and this is our presentation for the Merkle trees.
My name is Evan Colin. So first off, what is a Merkle tree? A Merkle tree is alternatively known as a hash tree. It is frequently used whenever you have a large amount of data that needs to be stored, encrypted, and somehow managed. Ultimately, it's just another data structure. The information isn't stored in a unique way, is what is done with that data, which is hashing, that makes it unique. You can go on to the next slide. When is a Merkle tree used? A Merkle tree is frequently used in the following. It's used in blockchain, it's used in GitHub to track changes to files, it's used in your very own operating system directory, your computer directory, and it's used anywhere that there's going to be large amounts of data that needs to be stored. You can move on. So why is a Merkle tree used? This is going to be the biggest section. You can compare large amounts of data and detect changes. It's useful in detecting updates to a database, and you can quickly find corruption to data. Now, how is this done? If you have a file or a folder that contains a file, that folder will not point directly to that file. Instead, it points to a hash of that file. So if the hash is done correctly, anytime the contents of that file changes, the hash will change. But if the file's contents don't change, then it should stay the same. So then the folder can see, well, if this hash changed, then the file obviously changed. So I need to change. So then the hash of the entire folder changes. So if another folder is pointing to that folder, it can see that the entire folder's hash has changed, so it knows that something within the folder must have changed. This is going to speed up finding any of the things that I've listed so much more than if you were to just go through every single file in your system or file directory, computer, software, whatever it is.
Okay, so I'm going to show you the visualization of the Merkle tree. So this picture shows the structure of the Merkle tree, and from this picture, and we can know that the Merkle tree is kind of the binary tree because every node only have the two children, and then the node stored hash instead of the value of the data. So and when we start off the 4 chunks at the bottom of the data, um, so the important thing that we have to notice that the data value itself is not a part of the Merkle tree. So hence before we construct the Merkle tree from the leaves, and we have to apply the hash function to all this chunk of the data. So the hash function is kind of the algorithm that we can convert the data into a hash value. And next we're going to talk about the parents node. The parent node is a little bit different from the leaves, and in order to create a parent node, we should take the concatenation of the left and right leaves and apply the hash function to that result. And this process will iterate until it reaches the top of the Merkle trees. And finally, we will get a single hash root will represent all these data. So next slide, I'm going to talking about some operation and the functions of the Merkle tree. And the first one is the construct function. From this picture, I'm going to show you the pseudocode of the implementation of the construct function. And for this picture, and we can obviously know that this function is recursive functions because we call itself at the bottom of the function body. So the first thing that I want to talk about is the parameter of this function is transaction. So the list of transactions stored all the value needed to be concatenated. So for example, let's take this image for example. In the first recursion that the transaction list contains all the values at the bottoms of the Merkle trees. So the next thing I want to talk about is the parameter of this, is the implementation of this function. The first thing what we do is we make the definitions of the base case. The base case is, in this base case, it said if the transaction set is equal to 0, and then we return this transaction, and it also means that the whole program is terminated. So let's get back to this image. For example, and we have the several transactions that need to be concatenated, and for every recursion that we concatenate all these values, and then we get this level, and then we get this level, and finally, if there is only one element and then left in the list, and then we finish this program. Okay, so I think that this function is pretty straightforward and very easy to understand. The next thing that I want to talk about is the data verification. The data verification is this operation is very important because it is readily used in the real world. Think about that if, for example, if you wanted to download video from the YouTube, and in the YouTube server, a unique hash value will represent the address content of that video. So before the download begin, the YouTube server will send you some piece of the data transactions, and then you're going to reconstruct the Merkle tree in your local machines. So and to make sure that the hash value is exactly the same as the root hash value of the video you want to download. So if the verification is true, and we start to download it, and otherwise it indicates that maybe some other program or the user attempt to split in some of the fake transaction into the bottom of the Merkle tree, and this may lead you to download some values from the other website. Okay, so let's take this as example. So let's assume that you have a record of the two in your local machines, and you want to ask the server to start the verification, and the server will send you the other information like the hash value of the 0, 1, 3, and 4, 5, 6, 7. So, and first of all, because we already know the hash value of the 2, and the server provide you the hash value of the 3, and with this information that you were able to compute the hash value of the 2, 3. And also with the hash value of the 0, 1 and the hash value of the 2, 3, you're able to calculate the hash value of the 0, 1, 2, 3. And with the hash value of the 5, 4, 6, 1 and the hash value of the 0, 1, 2, 3, you also can finally figure out what is the root hash value of this Merkle tree. So since you know that your record 2 is already existed in this hash value in the trusted server, furthermore, the system from which you have obtained the proof is proving to you that it is an authority because it is able to provide you a valid transaction or a piece of data from which you have. So in this way, you could able to construct this hash value, which represent the content addressing of the video you want to download. So any system that pretending to validate your request will not be able to provide you with this proper transaction. So from this example, and we know that the internet only needed to transfer a very little information about the trees for you to the verifications. And it is very efficient and it reduces a lot of time complexity and space complexity. Okay,